Okay, so trig substitutions. So we're going to be solving integration problems that have the square root of either a sum or a difference of two squares. So this first type, the square root of a squared minus x squared, this really comes from the trig identity. The one is equal to sine squared plus cosine squared, or if you solve that, 1 minus sine squared x is equal to cosine squared x. And so if you take the square root of both sides, you get cos x is equal to the square root of 1 minus sine squared. And so we're going to be using that a lot, that trig identity. So what you're going to do is you're going to think about trying to write this basically so it looks like a 1 minus sine squared. So we're going to take the 4 minus x squared, and we're going to try to rewrite it as, so let's just put a little box around this. This is something we want to keep in mind up here. So we're going to take that 4 minus x squared.
Mr. Morehouse,
Yes.
can you share your screen?
Oh, I'm so sorry. Yes. There, is that, there we go. You have to holler at me. Sometimes I'm just oblivious. Okay, so now that you can see what I'm doing, so we've got the our identity up here that we're going to be using a lot of in a little box. And then we're integrating this square root of 4 minus x squared. So I want to take this 4 minus x squared. I want to try to think of it as basically like a 1 minus sine squared. So the first thing I'm going to do is just rewrite it. I'm going to pull the 4 outside and write it as 4 times 1 minus x squared over 4, which is the same as saying it's 1 minus x over 2 all squared. And now that x over 2, I want to think of that as a sine. So I'm going to make the substitution x over 2 equals sine, and I don't want to use x's. I guess maybe I shouldn't have put x's in up here. Let's call these thetas instead of x's. Doesn't matter what our variable is, so we can rename it anything, but that'll just help us to not get confused between the x's and the u's and the thetas and the blah, blah, blah. There's so many variables running around. All right, so x over 2, we're going to call that sine theta. So if x over 2 is sine theta, that means that x is actually equal to 2 times sine of theta. And then that means that the dx in this problem would be equal to 2 times the derivative of sine, which is cos theta, times d theta. Okay, so now we make all of those substitutions in our integral. So we're going to sub in, and we get the integral of the square root of, let's see, I want to write that, we said the 4 minus x squared is 4 times 1 minus x over 2 squared, so this is 4 times 1 minus sine squared theta, and the dx becomes a 2 cos theta, and then we're gonna clean things up a little bit. That 4 square root can come out as a 2, and the 2 multiplied by that is going to give us a 4, and we're going to pull it outside the integral. And then the square root of 1 minus sine squared, that's that identity that we said we wanted to keep in mind. That's equal to cosine of theta. So we're going to have a cos theta from here, from this square root, and then we have this other cos theta here, so that gives us 2 times cosine theta times itself, so cos squared theta d theta. And then once we have that, we're just in the basic, this is an integral involving a trigonometric function, which we just covered in section 3.2. And so we use the techniques that we know from section 3.2 to finish off the last step. And sometimes it'll be a u substitution, maybe you'll have a sine and a cosine. Sometimes it'll be something more complicated, like the cos squared, where you have to use the half angle identity. But whatever, it's going to be just an integral with a trig function, which you know how to handle. And I don't remember the half angle identity for the cosine, so I might have to go back and look it up. Let's see. I think I have my OpenStax textbook here. Here it is. Back to 3.2. Half angle identities. Okay. So cos. Oh wait, that's not it. That's different angles. Cos squared is 1/2 plus 1/2 cosine of 2x. All right. So that would be 4 times the integral of 1/2 plus 1/2 cosine of 2 theta d theta. And so we integrate the constant function, and so we get a 2 theta 4 times 1/2, and then integrate the 1/2 cos 2 theta. We're going to have 4 times 1/2 times the integral of cosine is sine, and it's a 2 theta. So like if we, I'm not going to go through and write it all out, but if I did a u sub here and said u is equal to 2 theta, then my du is 2 d theta. So there's a 1/2 that I need to compensate for that 2. So that is our final integral. And then we can clean that up just a little bit. So we get 2 theta plus sine of 2 theta plus c. All right. Does that make sense? Are there any questions before we, I thought we'd do an example and I'll have you work through one Okay, then, so this is just a little reminder of where that, another way of thinking about that substitution, making the sine theta equal to x over a. It's kind of like you're thinking about your triangle. You have a square root of a squared minus x squared, and that's this side of the triangle, and then the other sides of the triangle are a and x, and sine of theta is the opposite over the hypotenuse, sorry. And so, oh yeah, sorry, that's what we're doing. I'm like, not quite with it this morning. So what we need to do now, we're not quite done, because if we go back up and we look at our original integral, that original integral was written in terms of x. And our answer here at the end is written in terms of theta. Well, that doesn't make any sense, because what does theta have to do with x, right? So I want my final answer, my original answer is an integral of a function of x, then my final answer should be an answer in terms of x. So that means I need to substitute back in for the theta and the sine of 2 theta. I need to figure out what those are as x's. So the theta is the angle in this triangle here. So for us, A was 2, and this is a 4. And so sine of theta is x over a, which means that theta is the sine inverse of x over a, or x over, in our case, 2. And so that gives us something we can sub in back here. So our answer, let's see, I guess we can write it down here. So our integral of the square root of 4 minus x squared dx then is, we said it was theta plus, no, 4 theta, 2 theta plus sine of 2 theta. So I substitute those in. 2 times theta, well, theta is sine inverse of x over 2 plus sine of 2 times sine inverse of x over 2. All right, so then that gives us an answer in terms of x, and we could actually simplify this even a little bit more. Sine of 2 times, oh, it's taxing my memory. I have to remember my trig identities. Sine of 2 theta, I believe, is so what's sine of 2 theta? I think it's 2 sine theta cos theta. I'm pretty sure that's the double angle formula for the sine function. So that means that we could write this as 2 sine inverse x over 2 plus 2 times sine of sine inverse of x over 2 times cosine of sine inverse of x over 2 plus c, and then sine of sine inverse of x over 2, that's just going to give me an x over 2, and the cosine so this piece is just x over 2. Cosine of sine inverse of x over 2, that is just cosine of theta, right? Because theta is sine inverse of x over 2. So if we go back up and we look at this triangle, if sine of theta is x over 2, cos theta, that's the adjacent side over the hypotenuse, that is the square root of a squared, well, let me make that a little bigger so we can see. That is the square root of a squared minus x squared over a, or in our case, the square root of 4 minus x squared over 2. All right, so that is our cosine of sine inverse, okay, square root of 4 minus x squared over 2. And then plus c. And we could cancel some 2's, but otherwise we're pretty much as good as it's going to get. All right, so that's a lot of steps involved in these integrals. You're making a substitution and you have to reverse the substitution at the end, but reversing the substitution gives you some trig functions of inverse trig functions, which you then need to go back to your triangle and figure out. So there's just a lot going on in these integrals. So here's the basic idea, though. You see that square root of something squared minus x squared. You should automatically be thinking of a trig substitution, but you want to first just check that it isn't something simple that you already know. For example, this is just a simple u substitution, right? The integral of x over the square root of a squared minus x squared. If I made u be a squared minus x squared, then my du would be a minus 2x dx, and that would be an easy problem to solve with u substitution. And I would not want to go through and do a whole trig substitution for something that could easily be done in another way. So just check that first. But then once you've verified that this isn't something that you really can do in another way, then you're going to want to just pull out your substitutions. So you make the substitution that x is a times sine of theta, so whatever a is, and then dx is going to be a cos theta d theta, and so that square root you get to replace with the cos theta, the a cos theta. Then simplify it as much as you can. Evaluate using the techniques that we've talked about from section 3.2, and then use your reference triangle to reverse the substitution. All right, so this integral of the 1 over the square root of 4 minus x squared, I don't know why they say that this type can be integrated directly. Oh, by a formula. So this integral of 1 over the square root of a squared minus x squared, I think that's one of the, in the table of integrals that we haven't really looked at yet, but we could. But let's do it using a trig substitution anyway, just because. So take a few minutes and think about what are you going to make, what substitution are you making, and then substitute in and see what you get after you simplify it as much as possible. So I'll give you like 2 or 3 minutes. All right, so have you decided on the substitution? Mauricio, I'll pick on you.
I kind of followed the same pattern as the last one.
Okay, so what substitution did you make? So what is x?
That'd be a 2 sine as well as the last one, or 2 sine theta.
Yep. So x is 2 sine theta, and then dx.
Yeah, 2 cosine theta.
Okay, and then what did you end up with once you made those substitutions in the integral? What did you get?
I didn't get that far yet.
Okay. How about you, Ramon? Did you substitute in?
Well, yes, but I moved the, is it perfectly fine to move the dx? Or no, I can't move the dx, can I? To
Move it
outside and
where?
make it, what?
No, you can't move it to the outside, but you can move it off the fraction if you like.
Yeah, sorry, that's what I meant. Move it off the fraction.
So you could put it over to the side and
Yes,
have your 1 over the square root of 4 minus x squared there, and your dx on the outside.
yes.
Okay. So you substituted dx is 2 cos theta d theta. And what's this fraction?
It's 1 over the square root of 4 minus 2 sine theta squared.
4 minus 2 sine theta squared, which is 4. If I square the 2, right, it's 4 times
Oh, yeah.
sine squared theta. Okay. So just to be clear, you didn't really move the dx outside of the integral. It's still inside the integral. It's just outside of, well, outside. It's just, it's not in the fraction anymore, but it's still being integrated. So you didn't take it outside of the integral.
Yes.
So now what are we going to do with that square root of 4 minus 4 sine squared theta?
We wouldn't, or well, we would, because we can't just, you can't just subtract it in there because they're not the same.
Nope. But those 4's are the same. So you can do something with those.
Just take out the 4s outside.
Yep. Bring the 4's outside. So this is the square root of 4 times 1 minus sine squared theta. And the 4 is 4 under a square root, right? So you could pull that out. And what can you do with that 1 minus sine squared theta? And this is really the whole point of why we make the substitution for x, the particular substitution that we chose.
Will that become cosine theta?
Exactly. Cosine squared, but it's under a square root, so that becomes a cosine. So in this parenthesis here, we have a 1 over cosine, oh, whoops.
2 cosine.
2 cosine, yes, theta. And we have a multiple of 2 cosine theta. And the 2 cosine theta in the numerator and the denominator can cancel each other out. So we're just integrating d theta. What's the integral of d theta?
One? No, wait, no. It'd be just theta, right?
It'd be theta. Yeah, it is a 1 that you're integrating there. It's kind of a hidden 1. And when you integrate it, you get a theta, and we always have to throw in that plus c. And now we have to do the reverse substitution again. What is theta? Well, we want to remember this original substitution. So if x is 2 sine theta, then what is theta? So basically you want to take that and reverse it, right? So solve this for theta.
That'd be just x over 2.
Sine of theta would be x over 2, yeah. So what does that make theta? So we basically just want to get rid of that sign, right? So how do you get rid of the sine function? Well, you need its inverse. So just like, you know, if you have, I don't know, 3x equals 7, and you're trying to solve for x, you do the inverse of multiplication by 3, which is division by 3. We don't think about it that way, but that's really what you're doing. You're using the inverse of the times 3. Well, here we're going to use the inverse of the sine function. So take sine inverse of both sides. And the inverse of, so sine inverse of sine of theta, the sine inverse and the sine, they're just canceling each other out. And that just gives us theta equals sine inverse of x over 2. And you don't really need to go through that every time, right? That's just, like, you just want to have that at your fingertips. That is always going to be the last step. Your theta is always going to be sine inverse of whatever the x over a, whatever your a happened to be. All right. So you're going to practice those. You're going to get lots of practice with those. And those aren't the only types of integrals that we can solve using trig substitutions, but we're going to need some different trig substitutions. So for instance, if we have the square root of something squared plus x squared, and we want to integrate something like this, you want to think about the other trig identities that you know. So we know sine squared plus cos squared equals 1. Well, we just use that one. So That's probably not going to be it. So I want to think about this more like the square root of a squared plus x squared. I want to think of it as a times the square root of 1 plus x over a squared. So I want to think about a trig identity that has a 1 plus something squared equal to something else. And when I start running through my memory of trig identities, I know that tan squared plus 1 is equal to secant squared. So that is the trig identity that we want to keep in mind here. So 1 plus tan squared theta equals secant squared theta. That's going to be useful for us in this situation. So we're going to make the x over a be a tangent. And that means then that 1 plus x over a squared would be 1 plus tan squared, which is secant squared. Whoops, secant squared. So the square root of a squared plus x squared would be a times the square root of secant squared, which is just secant. All right, so that's the identity that we're going to be using and the substitution that we're going to be using in all of these types of problems where you see an a squared plus x squared. That's what you're looking at. So here, the a is 3. And so the substitution that we're going to make is x over 3 is equal to tan theta, or x is equal to 3 tan theta. Which means then that the dx, well, I have to think about the derivative of tangent. Derivative of tangent is secant squared. And so now when I make the substitution in here, I'm going to get the integral of, so the square root of x squared plus 9, that's the square root of a squared plus x squared, is just a times secant theta. So this a is 3. This is going to be a 3 secant theta. And the dx is secant squared theta, or sorry, 3 secant squared theta, d theta. So this is dx. And that gives us to integrate 9 times the integral of secant cubed theta d theta and secant cubed. I have to go back. and look again at the 3.2 trig integrals. So secant cubed, how do we deal with a secant cubed? So if a is even and j is odd, then we use tan squared equals secant squared minus 1. And use integration by parts to integrate odd powers of secant. I'm not sure if that's going to work here. Let's see. So if we use the identity secant squared is 1 plus tan squared, does that help us? Or are we just using integration by parts? I think we just use integration by parts at this point and say this is a secant times a secant squared. The secant squared is the derivative of tangent. Secant, we can take its derivative and we get secant tangent. Let's try that. So I think maybe, so this is our trial here. We're going to try doing a u equals secant theta, and the dv is secant squared theta d theta. So v is tangent theta, and du is secant theta tan theta d theta, and then uv is secant tangent minus the integral of v du. I don't know. I'm not sure if this is going to help. Okay, so that would be 9 times uv secant theta tan theta minus the integral of v du so that's a secant tan squared I'm not seeing where this is going. Whoops, hold on. Move this over here where we're looking so I can find it. Okay, so if k is even and j is odd, then use tan squared equals secant squared minus 1 to write tangent in terms of secant. Use integration by parts to integrate odd powers of secant. Oh, so maybe we have to. No, that wouldn't work. Oh yeah, maybe this is one of those where we end up getting a secant, another one of the original integrals, and then we have to do some algebra to convert it. So if I wrote this okay, so we had 3 secant cubed. So if we write this tan squared as secant squared minus 1, does that okay? So this is 9 times the integral of, we've got a tan squared in here, and tan squared is secant squared minus 1. So we can rewrite this as secant squared theta minus 1 times secant theta d theta, and then we have a secant cubed minus a secant, so that's minus 9 times the integral of secant cubed theta d theta, minus a minus would be a plus, the 9 times the integral of secant theta d theta, and then the integral of secant theta, we have a formula for that. The integral of secant theta is the natural log of absolute value of secant x plus tan x. So we could replace that and then we can solve. We've got on the left side, we've got this 9 times secant cubed. So over here, this is 9 secant cubed integral. And that is equal to all of this mess. And so then if we bring all of the integrals of secant cubed together on one side, we can solve for that. That's an ugly mess, but yeah. But we can do it. It would have been nice if I had left out the 9s to begin with. It would have made things a little easier, I think. Let me do that. So let's say we really only want to know, just get rid of this 9, nope. Okay. So let's say we just want to integrate the secant cubed. Okay. I'm just going to drop all the 9s from everything. Just so I don't have to deal with that. Okay, and then if I take this, what I have, and move everything over to one side, so we're going to call this secant cubed I. And this integral of secant cubed is an I as well. So if I add I to both sides, I have 2 times I is equal to secant theta tan theta plus ln of secant theta plus tan theta, and now divide by 2. So I was the integral of secant cubed theta. So that says the integral of secant cubed theta is 1/2 secant theta tan theta plus 1/2 ln of secant theta plus tan theta. And then we can go back and make the reverse substitution for theta and for secant theta and for tan theta. Whew, that was a lot. So these are tricky integrals. I will say we're going through all of this, but a lot of these, there are tables of integrals, and you can find these, a lot of these on the tables of integrals, and you don't have to go through all of the rigmarole, but it is good practice to do that. All right, so all of this was a little aside because what we wanted was we wanted to get this 9 times the integral of secant cubed. So now 9 times the integral of secant cubed would be would be 9/2 secant theta tan theta plus 9/2 ln of secant theta plus tan theta, and sub back secant theta is what was it, x over 2, I think, x over 3. No, tan theta is x over 3. And secant theta, we'd have to draw our triangle and think about tangent, secant. That's a terrible triangle. And so if this is our angle and tangent is x over 3, tangent is opposite over adjacent, so this would have to be x, that would have to be 3. So then the hypotenuse would be the square root of x squared plus 3 squared, or x squared plus 9. And secant is opposite over hypotenuse, so that would be x over the square root of x squared plus 9. So you would, at the last stage, you would go back through and sub in secant theta is x over root x squared plus 9, tan theta is x over 3, etc. in each one of these spots. But I'm going to leave it because we're kind of out of space on this page, and that last step you can do. Okay, so that's the general problem solving method for integrating integrals that have a square root of a squared plus x squared in them. Again, you always want to just look and see if there's an easier way, because as you can see, this is really long and involved method, and if you can avoid it, then by all means you probably want to do that. If you can't, however, then you make that substitution. X is a tan theta, dx becomes a secant squared d theta, and then just substitute in for everything. That gets rid of the square root and leaves you with a secant theta, and simplify that as much as possible. Use the techniques to evaluate the integral, and then reverse substitute is step number 5. All right, so here's one for you to try, and we won't go through, well, I don't know, we'll see how bad it is, but we'll try this one and at least do the first bit of the substitution. So think about what you would want, how you would want to substitute. What is the substitution you're going to make for x? And then what's the dx going to be after you make that substitution? And you'll notice that this one's a little bit different than the setup. The setup is a squared plus x squared, and this isn't quite that, so you have to think a little bit harder on this one. So I'm going to give you 10 minutes because we really should have taken a break and we didn't. So I'll give you 10 minutes, we'll take a break, think about it a little bit, and then we'll come back and we'll do the, we'll finish this problem up. All right? Okay.
All right. Yep.
And you guys can talk if you want. I will leave so you can chat without me listening in. All right. It's been 10 minutes. Are you there?
I'm here.
All right. Okay, good. So we're all back from break. So what did you come up with as a substitution for this 137 problem? Ramon. I'll pick on you this time. Any ideas?
Did you want us to use the tangent or?
Yeah, it's definitely going to be a tangent substitution. It's just like what exactly, what's the A?
Well, I guess since it's a 1 and since it's not, because a 1 can be squared and it'd still be 1. So you'd be able to use tangent then, right?
So what's tangent? So essentially the idea is that I want this, what's under the square root, we want that to be a 1 plus tan squared is what the philosophy is, the strategy.
Oh, would x be 3 tangent theta?
Close, but not quite. So I want this essentially to become a tan squared.
Because tangent is equal to 1 plus, or no, that's secant.
So this one's a little bit different than the previous because the x has that constant being multiplied times it,
Mm-hmm.
but the idea is still the same, right? I want to when I make the substitution, I want to end up with a 1 plus tan squared. So if this 1 plus 9x squared is going to turn into a 1 plus tan squared, then that 9x squared, the whole thing has to be tangent squared, which means tangent is going to be what?
It's going to be this. It's going to be square root of 1 plus 9 tangent squared. No.
No. So I want what's under the square root to be a 1 plus tan squared. So just like up here, right, where when you make the substitution for the x is a tan theta, and then you can factor the a out, you end up with a 1 plus tan squared, and then you get to replace that with a secant squared, right? That's the idea. So I want this 9x squared here is going to have to be tan squared.
Mhm.
So if 9x squared is tan squared, what's tangent?
Yeah, 3x.
That's it. So that means x is tangent over 3, or 1/3 tan theta. So Mauricio, you had it almost right. It's just the 3 was in the wrong spot. And so then that means your dx is what?
Be 1/3 secant squared theta
Yep,
d theta.
exactly. Excellent. And then you can make the substitution. So the square root of 1 plus tan squared is a secant squared. So you have 1 over the square root of secant squared. The dx becomes a 1/3 secant squared. And now we just simplify that and integrate and then reverse substitute. So pull the 1/3 out front. Square root of secant squared is just secant. Divide one of those secants, or cancel one of the secants with the 1 over secant. And so this is just 1/3 the integral of secant theta d theta, and then you go to your table and you know the integral of secant theta. We already figured that one out, or looked it up, I should say. I didn't figure it out. Is ln of secant plus tangent, I think. Let me look. Ln of secant theta plus tan theta. And then you have to reverse that substitution again, right? You've got to go backwards to change the thetas back into x's. And the tan theta is easy because that was your original substitution. Tan theta is just 3x. But the secant theta, that's the one that's trickier. And that's where you need your triangle. So tan theta is 3x. And if I think of tangent, remember, is opposite over adjacent. So I draw my triangle. Opposite side is 3x. The adjacent side I'm going to make 1. So 3x over 1 is just 3x. And then the hypotenuse is the square root of 1 plus 3x squared, which is 1 plus 9 times x squared. And then secant theta is, secant is opposite, hypotenuse over opposite. Sorry, I think I wrote that wrong on the last one. Oh, maybe not. Maybe it was in the secant. No. I'll have to go back and look in the notes. So secant is hypotenuse over opposite, which is square root of 1 plus 9x squared over 3x. And then that's your final answer. All right. That one wasn't quite as bad as the last one. Okay. So then the last type is where you have, instead of, so this looks a lot like the first one, but it's a little bit different. So the very first type was an a squared minus x squared. Here it's just reversed. You have the x squared first minus the a squared. And unfortunately, you can't just use the same trig identity or trig substitution. So if you sub in x equal to sine of theta, then you'd have like a sine squared minus 1 type situation, and sine squared minus 1 is negative cos squared, and you can't take the square root of a negative, so that's out. So you have to use a different trig identity. And again, you want to think through the trig identities that you know, think about which one might fit in here. And we've used the sine squared plus cos squared equals 1. We've used the tan squared plus 1 equals secant squared, but there's another way to rewrite that. Tan squared plus 1 so that it has a minus in it instead. So if we subtract 1 from both sides, we get tan squared is secant squared minus 1. And so the trig substitution that you want to make for this is just x equals secant theta, or sorry, secant theta equals x over a. So the substitution is secant theta equals x over a, or x equals a times secant theta. And then if x is a secant theta, then the square root of x squared minus a squared becomes, whoops, I made my little square root sign too big. So the square root of x squared minus a squared becomes the square root of a squared times secant squared minus a squared, and we can pull an a out of that. Secant squared minus 1, I get to replace that with a tan squared, and then take the square root of tan squared. Oh, whoops, and this isn't an a. This is, sorry, this isn't an a squared, it's just a, because I pulled it out from under the square root. So we get a tan theta. Okay, so that's our x substitution, and then the dx derivative of secant, sorry, is secant tangent. D theta, oops. And so we substitute all of those bits in, and this becomes the integral of dx is a secant theta tan theta d theta. The square root of x squared minus a squared we figured out was a tan theta. And so the tan thetas cancel and the a's cancel. And that's just secant. And then we use that same formula. The integral of secant is ln of secant theta plus tan theta. Then we reverse the substitution. So secant theta is x over a, but then we have to think about the tan theta. So if secant theta is x over a, again, I think about my triangle. Here's theta. Secant is hypotenuse over opposite. That's x over a. So this is x and this is a. And that makes this leg, we use the Pythagorean theorem, that is the square root of x squared minus a squared. So tan theta, which is opposite over adjacent, is a over the square root of x squared minus a. Minus a squared, I should say. So secant is x over a, and tangent is a over the square root of x squared minus a squared. All right. So that's a tangent trig substitution, or a secant trig substitution, I should say. So the general situation when you want to make the secant substitution is when you have square root of x squared minus a squared. Again, you always just check to make sure that this isn't something you could do with a simple u substitution. And assuming that it's not, you're going to make x be a secant theta, dx then is the derivative of secant, it's a secant tangent. The square root simplifies to just tangent, and then you do whatever you have to do to simplify, evaluate using techniques of trig integrals, and then reverse the substitution at the end. All right. So I think we'll skip this one and just go to, because I feel like the harder part, well, sometimes the harder part is figuring out which method to use when you're looking at an integral, like which type is it? And so for each one of these integrals, I want us to just think about what substitution would you make? So for each one, try to just go back through your notes and look and see which substitution would you want to use for each one of these integrals. And I can zoom out a little bit, whoops, out, not in, so you can see them all. And these are somewhat simpler than the cases we've been talking about. The a in each one of these is 1, So you're not worrying about what your multiple is. They all have the same multiple. So take a few minutes and think about that. All right. I know I probably didn't give you quite enough time, but I do want to jump on the very last bit of this section. So for 154, what substitution do you want to make for x?
Would this first one be, would the first one be the using the secant to substitute?
Yep, exactly. So x would be secant theta, which means dx is, I have to remember the derivative of secant,
Secant tangent theta?
yep. So secant theta, tan theta, d theta, and then you substitute in and you would just have a tan theta to integrate. All right, how about the next one? What would we want x to be here? Mauricio?
Will this be a tangent?
Nope.
Sine.
Yeah, there you go.
Yep.
So think of the, 1 minus sine squared equals cosine squared. So your x would be sine theta, which means your dx is, cos theta. And then square root of x squared minus 1,
Yeah, secant again.
a secant again, exactly. So this one's a secant. This one's also a secant. And this one,
That one be a sine again.
so maybe. I don't know, there's no square root in it, so I'm thinking, let's see, if x is sine of theta and dx is cos theta, oh yeah, so that becomes, that would become cos theta over cos squared theta, which is a secant theta, and then you'd have to use the formula to integrate that. How about this last one? Second to the last one.
Would we use tangent for it?
Yep. And if x is tan theta, then dx is secant squared d theta. All right, so basically you're just looking for, you know, is it a plus or minus, first of all? If it's a something plus something squared under the square root, it's a tan theta substitution. If there's a minus sign instead of a plus sign, you're either going to use sine or secant, and that just depends on whether the x is in front or the constant is in front. So if it's the constant minus x squared, you use sine, and if it's x squared minus a constant, you use the secant. And this last one is tricky. So this kind of looks like what we've been talking about, but not quite. And basically with problems like this where you like at first you might just look at it and say, oh, it's probably a u substitution, but there's no du. If you try making u be x squared minus 6x, that doesn't work. So then you might start running through your head and thinking about all the different techniques you know, and trig substitution doesn't look like it would work here because you don't have the right format. Like it doesn't have an x squared minus a squared or a squared minus x squared. But what you can do with these types of problems is you can complete the square to rewrite it as something that does have the right format to be a trig substitution. So you write that x squared minus 6x, you want to write it so that it's a perfect square. But what do you need to add to that to complete the square? And then whatever you add, you have to take it away. So what would make x squared minus 6x be a perfect square?
Would it be 36?
No, not quite. So that would be taking that 6 and squaring it. But what you really want to do is take 6 over 2 and then square it. So divide by 2.
9.
And then square. Yep. So x squared minus 6x plus 9 is a perfect square. We can't add in 9 to the problem without changing it. So we add a 9 and we subtract a 9. And now what we have is x minus 3 squared minus 9. And if I think of that x minus 3 as like a u, this is like u squared minus 9, which is a trig substitution situation, right? In that case, if you had u squared minus 9, you would make the trig substitution u equals 3 times secant theta. But in this case, we have x minus 3 squared minus 9, so we're going to make x minus 3 equal to 3 secant theta. So x is 3 plus 3 secant theta. And then you go from there. So we can rewrite the integral. I don't know if I gave myself enough space. We can rewrite this integral as the integral of 1 over x minus 3 squared minus 9 dx. And then we make the substitution, x equals 3 plus 3 secant theta. So dx becomes 3 secant theta d secant theta tan theta d theta. And this x minus 3 squared minus 9 becomes a tangent squared. So this is 1 over x minus 3 is 3, so it's 1 over 3 tangent squared dx becomes 3 secant theta tan theta d theta, and then you can cancel one of the tangents and rewrite that as secant over tangent, which I would probably just rewrite in terms of sines and cosines. So tangent is sine over cosine. I'm trying to squeeze this in here, and I know I'm not going to have enough space. So this would be 1 over, let's see, cancel out one of the powers of tangent and cancel the 3's. And secant is a 1 over cosine. And tangent is sine over cosine. So when you divide, when you have sine over cosine in the bottom, that's like flipping it over. So cosine over sine times 1 over cosine. And then the cosines can cancel, and that's the integral of 1 over sine, which is cosecant, and there's a formula for that. It's similar to the formula for the integral of secant. It's like ln of, and maybe there's some negative signs in there. I don't remember it, to be honest, but something like the natural log of cosecant and cotangent something. And then you do the reverse substitution and blah, blah, blah. The process from here on is basically the same. So I'm gonna leave that one because what I really want to talk about is the completing the square. So let's think about these and think about how to complete the square in each of them, and then what the substitution would be that you would want to make in each case. So for the first one, 1 over x squared plus 2x plus 1, what do you need to complete the square there? It's kind of a trick question.
Isn't that one already a perfect square?
Exactly. That's why it's kind of a trick question. Because it's already a perfect square, so you don't need to complete the square, right? That's already 1 over x plus 1 squared dx. And that one, you wouldn't really want to use a trig substitution because it's not in the right format. So you can't use a trig substitution, but it's actually much easier than that. What would you want to do with that one?
Can't we just simply integrate it?
What do you mean by simply integrate it?
Like, do a basic integration on it?
So how do you integrate 1 over a rational function?
No.
And it is not a difficult integration, but it's you can't just use like a power rule. Not yet.
This isn't by parts, is it?
Nope. Much easier than that. So it's almost a simple integration in Ramon, but you have to do one little thing first. One substitution. So I would just do a basic u sub. What do you want u to be, though? That's the question.
U should be x plus 1.
Exactly. And then that becomes a 1 over u squared, or just u to the minus 2. And then you can use the power rule on it, right? Then it's just a simple a simple integration from that point on. So yeah, that one's not bad, and it doesn't need a trig integral. So you really want to look out for things like that, like, oh, it's already a perfect square, I don't have to do anything. So, you know, make your life easy. Let's see, this one's a little bit trickier. So minus x squared plus 2x plus 8, I want to rewrite that so that I have a perfect square. This essentially, you kind of want to just think about this part and what you need to do to make it into a perfect square. So I would kind of start there and take that minus x squared plus 2x. Maybe I should use a different color or just put a line here. So minus x squared plus 2x. Shoot. Now it wants the whole thing. So what do we want to do with that? Well, the very first thing I would say is just pull the minus out front and write it as x squared minus 2x. And then I want to complete the square here. So what do I need to add to complete the square? So Ramon, you you just told me last time that x squared plus 2x plus 1 is a perfect square. So what do I need to complete the square for x squared minus 2x?
1.
Yeah, we just need a plus 1. And then, as always, you can't just add anything in that you want. You have to also subtract it out. So, and then this is minus x minus 1 squared minus 1. So distribute the minus. That's minus x minus 1 squared plus 1. So in the integral, we're going to have to set these aside for the moment. Maybe we won't do those, actually. I think just 2 examples is probably good enough. So now this integral, we're going to rewrite it as the integral of 1 over the square root of minus x minus 1 squared, and then there's a plus 1 and a plus 8 dx. Let's just put the dx up top. So that becomes the integral of 1 over 9 minus x minus 1 squared. And now you can make make the trig substitution. You want x minus 1 squared to end up being your sine squared, or your, well, 9 sine squared. So you want x minus 1 to be equal to 3 times sine of theta, and that means that x is 1 plus 3 sine theta. And then you substitute in and you make the simplifications, etc., etc. So we won't go through the rest because we're out of time. Actually, 5 minutes over. Sorry about that. All right. So I know these are, they're tricky. I kind of like them though. I sort of think they're like little puzzles to figure out, but they can be somewhat painful little puzzles to figure out. Sometimes not such little puzzles.